In this lesson, we're going to be talking about classifying matter as acids, bases, or neutral compounds. There's a couple properties of each of these compounds that we're going to talk about, and we're also going to define what the pH scale is and how you can recognize and name both acids and bases. This line here, we're going to draw a pH scale on it. All matter can fall onto this pH scale and be classified as an acid, which I'm going to highlight in red, a base, which I'll highlight in blue, or a neutral compound, which I've highlighted in purple. The acidity of a compound is measured on a pH scale. The pH scale right in the center gets the number 7. Compounds that are at a pH of 7 are considered neutral compounds. As you move towards the left, compounds become more acidic. The further away from 7 you get, the more acidic your compound is. So you could put 0 on this end, but truthfully, you can actually get an acid with a pH below 0. That is possible. But conventionally, we go from 0 on this end, 7 in the middle, and 14 on the other end. The further above 7 you get, the more basic you are. So I'm going to put bases on this end. Just to show that this scale shows the strength of an acid or a base, closer to the 7, I'm going to say these are weak acids or weakly acidic, and these are more strongly acidic. Same thing can be said for bases. If you are close to 7, you are weakly basic. And if you are further away from 7, then you are strongly basic. Here's some different substances and their relative pHs. Water fits right on the 7. Water is a purely neutral compound, pure water. The water that you're going to get from a tap will be likely slightly acidic, though that depends on what's dissolved in it. If it was pure water with no solutes in it at all, it would be a pH of 7. Close to neutral are milk and blood, milk being very slightly acidic and blood being very slightly basic. Some stronger bases would be like some hydroxide-based drain cleaners or some pure hydrochloric acid, strongly acidic. Lots of foods fit in our acidic category. Lemons, apples, vinegar, tomato, banana. Lots of fruits are acidic in nature, with a lemon being more acidic than, for example, a banana. Some properties of each of these. Acids. Now, I don't recommend that in the lab you taste acids, but lots of foods are acidic in nature, and they lend a sour taste to a food, whereas a base will taste bitter. Not as many foods fit in this basic category because, in general, we don't like the taste of bitter things. However, we do have a couple foods that would fit over here. Baking soda is a slight base, not that that's necessarily a food that people just eat. There's not a particular touch sensation for acids, so I'm just going to put a line through here. There's not a particular way that an acid is going to feel. Again, it's not always best just to touch these things because they can be quite corrosive, both acids and bases. But bases, weak base, if you think about how a soap feels in your hands, these are going to be slippery. Bases are slippery to the touch. Acids are going to react with metals to produce hydrogen gas. I'm going to say react to produce hydrogen gas. Hydrogen is a diatomic element, so I'm just going to put H2 and then the little G to show that it's in the gas state. Bases don't have a specific reaction with metals, so I'm just going to draw a line through this box. We do a test for acids and bases using an indicator called litmus. You're going to see these little litmus papers. I'll do a lab in here as a demonstration. A piece of litmus comes in two colors. There is a red litmus paper and there is a blue litmus paper. To test for an acid, blue litmus paper will turn red. So blue litmus turns red. That will indicate that a solution is acidic. The test for a base will be kind of the opposite. Red litmus paper will turn blue. And that lets you know that a solution is a base. Both of these produce ions in solution, which means both acids and bases are conductive. So electrical conductivity of solution, they are conductive. We're going to write conductive, which means electricity will pass through. In contrast to molecular compounds in solution, which will not be conductive. This is based on the pH scale above. So if we look at our scale real quick, anything below 7 is an acid, anything above 7 is a base. So the pH of a solution that's acidic is going to be less than 7. And the pH of a solution that is basic will be greater than 7. Some examples of acids and bases. Most acids are going to start with H or end with COOH. So some examples of some acidic compounds that you might see would be HCl. This is hydrochloric acid. Or acetic acid, CH3COOH. Both of these are acids. These are actually pretty common acids. HCl is hydrochloric acid. This is also stomach acid. And CH3COOH, acetic acid, this is vinegar. Those are pretty common acids. Most bases are going to contain OH in it. So a base like NaOH, this is sodium hydroxide. This is used as a drain cleaner, a strong cleaning agent. This is actually called lye commonly. Sometimes it's potassium hydroxide, but it is a strong base. Most bases are going to contain that OH minus. Naming acids. Here's what you need to know about naming acids. Acids are hydrogen compounds which are going to produce H plus ions in solution, hydrogen ions in solution. Acids form ions in solution, which means that they are form ions in solution and they're electrically neutral like ionic compounds. This phrase means that the number of hydrogen ions must neutralize the anion's negative charge. There should be a little apostrophe here because that negative charge belongs to the anion. So if we take a look at a type of acid, for example, this is going to be called sulfuric acid. I'll show you how to name it in a moment. Sulfuric acid is H2SO4. The reason for that is because sulfate has a 2- charge, and each of those hydrogens are an H plus ion. So kind of like an ionic compound, you have to balance the number of hydrogen ions with the negative charge on the anion. So you need 2 hydrogen ions for every sulfate in sulfuric acid. That's what this sentence is saying here. Because they form ions in solution, they're also conductive. So I'm going to write that underneath here. They also form ions in solution, which means they're going to be conductive. They will allow electricity to pass through the solution. Acids are named according to the hydrogen compound that is dissolved in water. Specifically, they're going to be named based on the anion. So I'm actually going to put that note here. It is going to be based on the anion. So if we're saying that an acid kind of acts like an ionic compound with H plus and an anion, because all of these acids are going to have hydrogen ions in them, we don't name them based on those hydrogen ions. The name changes based on what that hydrogen ion is paired with. Some acids contain polyatomic ions. These, like all other acids, form ions in solution. This is an example of a polyatomic anion. Rules for naming acids. Identify the acid by having an H at the beginning or a COOH at the end of the molecule. Since all acids are soluble in water, make sure that you have the subscript AQ to indicate aqueous. These are going to be in solution. 2 exceptions for acids. I need to write these down here. Exceptions. And I know it's annoying to start already with some exceptions. H2O and H2O2 are not acids. This is pure water. Yes, it starts with hydrogen at the beginning, but we don't consider it an acid. And H2O2, this is hydrogen peroxide. It does start with H at the beginning. It's not water, but treat it like a molecular compound, not like an acid. Compounds that have H at the end, lots of molecular compounds fit in this category, are not acids unless it's a COOH. So if you see something like methane, CH4, yes, it's a hydrogen-containing compound, but this is not an acid. The hydrogen is at the end, and it's not a COOH. So CH4 is not an acid. Here's how you're going to name acids. Remember that before we said that we name hydrogen compounds kind of like an ionic compound, where you just say hydrogen and then the name of the anion. Depending on the name of the anion, you're going to name it as an acid name a little bit differently. I'm going to highlight parts of this name. Let's do an example here. So if it was aqueous hydrogen and then something ending with "ide," we'll do an example. We'll do aqueous hydrogen chloride. Aqueous hydrogen chloride. The formula for this would be our hydrogen and then our chloride anion. And because it's an aqueous solution, we'll put the aqueous little state here. This is the compound name. HCl, hydrogen, chloride. Put those two together. That's probably a review of something that you have before. This gets changed into an acid name. If the ending was "ide," I-D-E. So for example here, chloride, the anion, ends in "ide." Then we change this acid name to hydro, whatever the root is, ic acid. The root is chlor here for chloride. So this is now going to be called hydrochloric acid. So a couple pieces in different colors here. The red piece, aqueous hydrogen compound, that's how we know it's an acid. Chloride ends in "ide." That "ide" ending becomes the hydroic ending. And then the type of anion was a chloride, so it is chloric acid. Where that becomes confusing is because we have a lot of different polyatomic ions which sound really similar to each other. So there's also such a thing as aqueous hydrogen chlorate. Aqueous hydrogen chlorate. I'll just draw what that would look like in this middle box here. We've got a hydrogen. Chlorate is ClO3, and this would be aqueous. This is aqueous hydrogen chlorate, HClO3 aqueous. It has this ate ending. The ate ending becomes the ic ending. So this is going to be called chloric acid. I know that sounds really similar to the hydrochloric acid, but the hydroic ending tells you that your original anion ended in "ide." If it's just ic, then your original anion ended in "ate." Finally, we have some polyatomic ions that are going to end in "ite." So if you had aqueous hydrogen chlorite, I'm just going to write the name out first. This "ite" ending, aqueous hydrogen chlorite, would look like HClO2 aqueous, because chlorate is the ClO3 minus anion and chlorite is ClO2 minus. This compound with the ite ending, ite becomes us. So this is going to be called chlorus acid. There are 3 possible endings to an anion. If it ends in "ide", then it's hydroic acid. If it ended in an "ate", which is many of the polyatomic ions, it's going to be just ic acid. If it ends in "ite", then it's us acid. Ate and ite are endings for polyatomic anions only. Ide is often for elemental anions, but sometimes also for some of the polyatomic anions. We're going to do an example of working both directions. So if you get a formula and now you are trying to work towards the name, what you should do is first identify that what you're looking at is an acid. We know this is an acid because it starts with hydrogen. This, therefore, is our anion. So I'm just going to break it down into its 2 ions. We've got H+, and we have CO3 2-. Then I'm going to figure out what's the name of my anion. If I look at my table of polyatomic anions, or polyatomic ions, this is carbonate. Carbonate has the ate ending. If I look at my acid naming rules, the ate ending has to change to the ic ending. So I'll keep the root here, carbon, but now it becomes carbonic instead of carbonate. Carbonic acid. This was called, I'll just complete this, this was called hydrogen carbonate. Yes, it's aqueous, so aqueous hydrogen carbonate, and it's now changing into carbonic acid because the ate ending becomes ic and the word acid is at the end. You can also identify an acid if it has the COOH at the end. Don't get confused though, because the COOH, the COO is actually going to be part of that polyatomic anion. So really I'm just going to highlight the H here, because the ions that are involved here are going to be C6, H5, COO minus, and H plus. Normally the cation goes first. In this particular compound, and in compounds that contain the COO minus, the H goes at the end. The reason that it's written that way, we're not going to get into too deep in Science 10, but this conveys something about the structure of what this molecule actually looks like. In any case, this anion is called benzoate. So this compound would be hydrogen. You can find that in your table of polyatomic ions. This is hydrogen benzoate. It has the ate ending, so we're going to change it to the ic ending. So this will be benzoic acid. Benzoic acid. If you're working backwards, this is if you're going from the formula to the name. If you're working backwards, we're going to skip hydrochloric acid because I already said that hydrochloric acid is HCl up here. But if we're working backwards from a name, let's look at nitrous acid. The first thing I want to identify is what was my new acid name? It was us. It was us. Us must come from the ending ite. The root stays the same, so this would be coming from a nitrite. This would be coming from a nitrite. The word acid, remember, means H+, so now I have to make a compound that balances H+ with nitrite. Nitrite you can find in your periodic table as being NO2- aqueous. It's got a 1- charge. Hydrogen ions carry a 1+ charge, so the balanced formula for this acid will be HNO2 aqueous. We need 1 hydrogen for every 1 nitrite. We know it's nitrite because the ite ending gets changed into the us ending for the acid name. Don't get confused when you see hypo instead of hydro. This is not the same thing. This is not hydrochlorous acid. This is hypochlorous acid. And so this is actually all part of our root for our name, hypochlor. We have that us ending, which means what we're looking for in our table of polyatomic ions is going to be hypochlorite. You can find hypochlorite in your table of polyatomic ions. And you will find that hypochlorite can be written as ClO- or OCl-. If we're going to balance either of these ions with H+, we can get 2 different formulas for this acid. Both are acceptable. We can have HClO aqueous or HOCl aqueous. Because in your table of polyatomic ions, both of these are written beside hypochlorite, either of these is fine. There's some good practice for naming acids here. I would encourage you to pause the video and try naming some of these acids. This is working from the formula to the name, so identify the anion, figure out what sort of ending you need on your name, write your name out. This is working from the name to the formula. The answers for these are right below here, and this is how the naming rules table looks like on your data sheet. It's saying the same thing. So if it ended in ide, it becomes hydroic. If it ended in ate, it becomes ic. If it ended in ite, it becomes us. And we have an example for each of these. Now we're going to go to strong bases. Think of a strong base as being an ionic compound with, we're going to say a strong base is basically an ionic compound with hydroxide. With hydroxide. You'll identify a strong base because it will have that hydroxide polyatomic ion. You'll name them just by using the IUPAC rules for ionic compounds. So you're going to name the cation first, and then the anion, and then you can determine the solubility using the table like we did in the last lesson. For naming this compound, we just identify what our cation is and what our anion is. This is no different than naming an ionic compound. Ca is calcium, and the anion here is going to be hydroxide. The presence of this hydroxide anion tells us that this is going to be a strong base. Sodium is our cation here, and our anion is hydroxide, so we'll name it just like we'd name a ionic compound. This is just simply sodium hydroxide. Here's a little table that talks about a few different common acids and what they might be used for. Hydrochloric acid exists in your body right now. It's what your stomach acid is made out of. It's what makes your stomach acid acidic. There's other things in there too, like enzymes. That's more of a Bio 20 discussion. H2SO4 is sulfuric acid. Sulfuric gets that ic ending because sulfate has the ate ending. This is commonly used in batteries, especially car batteries. This is going to be lead oxide mixed with sulfuric acid. H2CO3, this is going to be carbonic acid. Again, this is the carbonate anion. This forms naturally when you dissolve CO2 gas in water. So carbonated water like pop, soda water, bubbly, it will be acidic because of this carbonic acid. This is acetic acid. The reason it's called acetic acid is because this anion here is called the acetate anion. The ate ending turns into ic, and that's vinegar. Some common bases. Sodium hydroxide is the one I want to focus on here. It's sometimes called lye or caustic soda. It's used in a lot of different cleaning products. The reason I want to focus on it is because it has that hydroxide group here. Sodium hydrogen carbonate is a weak base. You can write weak base under there. In Science 10, I don't care too much if you can recognize weak bases. That's more of a Chemistry 20 concept. It doesn't have that hydroxide, so you don't see an OH minus group on here, so it's hard to recognize that this is a weak base. This one you should be able to recognize as a base. So for the purposes of Science 10, be able to recognize that an ionic compound with hydroxide is a base. If you didn't immediately look at this and be like, oh yeah, that's a weak base, I don't blame you. It's not easy to tell without doing experimental evidence to see that this would test as basic and turn red litmus blue. But this is the formula for baking soda, which is a weak base. Take a moment and try and decide whether or not these following compounds are acids, bases, or neutral compounds and explain why. I'll give you a minute to try and figure that out, so pause the video. And if you're back, now I'm going to work through it. You see that this compound starts with the hydrogen ion, so this is going to be an acid. If you tried naming it, this is going to be nitric acid because this is the nitrate anion. This compound here does not have a hydrogen group, and it does not have a hydroxide group. So this is going to be neutral. This is sodium sulfate, neutral compound. This one has that hydrogen group, so it's going to be an acid. The compound, or the anion here, is the nitrite, so this would be nitrous acid. And finally, this last one, because it has that hydroxide group, is going to be a base. This is barium hydroxide, named just like an ionic compound. This is an overall review of the different properties that you can expect with different compounds. We've got 4 types of compounds that we've looked at so far. We've looked at acids, neutral ionic compounds, neutral molecular compounds, and bases. Examples of acids will be something that starts with H, like HCl, or something that ends with the COOH, like acetic acid. Remember that acids will get the aqueous state because these are going to be dissolved in solution. Neutral ionic compounds will be things that don't have an H at the start and don't have an OH minus or a hydroxide at the end. So sodium chloride is a good example here. Most of these are going to be solid unless you dissolve them in water, which you have to check your solubility table for. Neutral molecular compounds are going to be combinations of nonmetals that don't fit in the other category. So you could have, for example, your glucose molecule, C6H12O6. That's going to be a neutral molecular compound. But you can also have something like methanol, CH3OH. It doesn't have the double OH. This is a molecular compound. Bases will end in hydroxide, or there's that baking soda weird base, but we'll focus on the ones that end in hydroxide, like sodium hydroxide here. For a litmus paper check, if you put blue litmus paper in acid, it will turn red. If you put either color litmus paper in a neutral ionic compound, there will be no color change. If you put either litmus paper in a neutral molecular compound, there will also be no change. That's because these compounds are neutral, and the litmus paper is a test for acid or base. So neutral in this context is talking about, is it an acid or a base? If you put red litmus paper in a base, it will turn blue. Think bases, blue, both start with B. For tastes, the acids will taste sour. Ionic compounds don't have a particular taste. You might think, oh, they're going to taste salty because sodium chloride is salty. That's not true for all ionic compounds. And then molecular compounds, this is going to taste sweet. This is quite toxic, so they don't have a characteristic taste. Bases, however, will taste bitter, which also helpfully starts with a B. So if you remember that bases are blue and they taste bitter, all of those words start with a B, which is nice for remembering their properties. Is it an electrolyte? An electrolyte is a solution that conducts electricity. In order to conduct electricity, you need to have ions. Acids will form H+ ions in solution, so they will conduct electricity. Ionic compounds have ions. This is a sodium ion and a chloride ion, so they will conduct electricity. Molecular compounds do not form ions, so they will not conduct electricity. They are not conductive. Not conductive, because there's no ions in solution. Bases do form ions, so they will also be conductive in solution. The only one that is going to react with metals with a characteristic reaction is going to be our acids, which will react to form H2 gas. Bases don't have a characteristic reaction with metals. In the next lesson, we're going to use this table of properties to identify some mystery solutions using these tests for litmus paper and conductivity. I don't think I'm going to taste any of the solutions, but that will be our next lesson.